Thank you everyone for coming. I'm Tony Moor, as Josh very politely says. Okay. I'm going to talk about some of my... Okay, thank you. Does anybody have any experience in silicon devices? Or actually looking, do you know what a chip actually looks like inside? Yeah? Good. That's a good start. I may pick on you, so don't talk too. But if you have any questions, please just shout out, and we can discuss them at the time. I think makes things more relaxed things for me. Just as an introduction of my sort of career in the last sort of 18, 19 years. So I started off in failure analysis. So looking inside semiconductors, looking for faults in the processes, developing the processes. And that was a good introduction into basically what is a chip and learning how to take it apart. Then I moved on to reverse engineering. So this is the legal side of hacking. So it's a company that wanted to make solutions for printer ink, video game accessories. Basically, if you want to protect your market for printer ink or video game accessories, you just put a very secure silicon device in there. To be able to make a compatible product which doesn't damage the platform, you can do that quite legally. You just have to go through a lot of hard work to reverse engineer the device itself and work out the encryption. And then once you do that, you put your solution in another device equally as secure, because you don't want everybody to have the secrets. So that was 10 years of that. Then I moved into South France, and we were doing security evaluations. Basically, same sort of thing, same sort of techniques, extracting data from devices to show the customer how it can be done. Kind of penetration testing of silicon devices, basically. Now I'm back in failure analysis with a UK-based semiconductor company. Okay, so that's probably what most people think of when they see a chip. It's just basically a black box with the connections, which is very true. It's how they all look. But if you open one up, what I would do is I would just basically, it's like having a cake. You have no idea what layers are inside the cake because it's covered in the icing, frosting, whatever you want to call it. But to have a look at the layers, you want to cut it open and take a look. So that's what we do generally to get a good idea of what's inside this package. So you do this with kind of abrasives like sandpaper, but very fine quality sandpaper. We cut it open, and this is what we see. So bear with me. It's difficult to talk about what was valid 30 years ago to today without actually talking about what a chip is. So apologies if it's a little bit obvious, or also if it's a little bit too much, too heavy. So if we cut open the package, this is what we see. So if you can see my pointer, can you see my pointer? Yeah. This chunk there, that's the actual silicon device. This is glued onto kind of like a heatsink with some conductive paste, which is this white or silver glue here. We zoom in, we see that there's a wire coming off. This is how the wire talks to the outside, the chip talks to the outside world. It's bonded onto the device there, and it travels to the pins on the outside of the chip. That's how it communicates. And if we look at the close-up in the top, there's something going on here. But the bulk of this is just silicon substrate. This may be 300-400 microns thick. But the interesting stuff is at the top here. It will all become clear, don't worry. Right, so this is a scanning electron microscope picture of a cross-section of this very thin crust on the chip. And we can see what's going on. This is basically, imagine it as a circuit board miniaturized. Everything here is glass. It's an insulator. Everything here, everything that glows basically or is brighter than the background, is conductive. So we have the metal tracks, which are made of aluminium in this case, and then we have the interconnect between the layers of circuitry, and they're tungsten. This is an older device. So yeah, it's like a transport system. You have one set of circuitry going in one direction and one going in the other direction, and you have these vias which connect the different layers of circuitry. And that's how the signal gets around the chip, basically. Interesting part of this, though, is right at the bottom, and these are where you have the transistors, and this is where the computation takes place. There's no point having all of this circuitry without having something that can manipulate the signal. So it's a very, very basic look at what this is a pair of transistors here on the right with the various components sort of named. And what I'm getting to is if you look at this dimension here, this is the smallest feature on the device, and that's what dictates the technology node, or the geometry of the chip that people refer to. In this case, it's roughly 180 nanometers. So you'd say that was a 180 nanometer process that they used to fab the chip. So we go to Moore's law. That's no relation to me at all, but this guy's pretty clever. And then back in 1965, he kind of revised it in 1975, I think, but basically it was that the amount of transistors would double in a chip every 2 years. The density of transistors would increase by 2 every 2 years. And he's pretty much spot on. It's not been it's got to stop at some point, you would imagine, but people were saying this 25 years ago, and it's still true. So Gordon is the man. So the takeaway from that, kind of see roughly what a semiconductor device is, and how the geometries have shrunk over the years. That has made things more difficult because, well, I'll go into it in more detail, but the natural evolution of the semiconductor industry has shrunk rapidly, of course, because we want low power, we want high performance, and that security devices have followed that as well. So it's not an intentional thing to make things harder. It's just something that's happened to the industry over a lot of years. So to summarize, this is how we look at the chip from the top down. This is the floor of the device, so there's no circuitry on there. Hard to believe, but there is nothing on there other than the silicon footprint of the device. So this doesn't work anymore, this chip, but it's just really to demonstrate what is present on a semiconductor device. So it's like I would describe it like a PC. Basically, it's a small computer in a very small package. It has ROM, it has flash, it has RAM, and it has CPU. It's very easy to spot where the memories are here. So the very regular rectangular boxes of different colors. These are the memories. One may be flash. These are ROMs. These are RAMs. And you may be wondering where the CPU is. Well, that is everything here. Everything in between is basically a sea of gates, which, well, in here you've got many hundreds of thousands of transistors that are doing all the computational work and taking data from memory to memory, basically running the device. So it's basically a CPU in its most basic form. So you have, within the logic C, there could be, say, over 300 different designs of cells, or a library of 300 designs of cells, all having very different functions. But within those functions, you could have many, many different designs specific to what you wanted to do. You could have a NAND or a NOR. It could be 20 or 30 different actual designs of that cell. Essentially, it's doing the same job, but it might be making the signal stronger, it has to pass further along the chip, or it has to be faster, whatever. But there's a lot of work goes into creating these designs, of course. But they get repeated on different versions of the chip, different families of the chip. They evolve over time, but yeah, it's there's an example on the bottom right of basically what we look at when we look at a standard cell. It looks like a bunch of 4 transistors working together. So look at the left there's 2 chips. One is from a much earlier period in time, not an awful long time ago, maybe 25 years ago. That might have been a new device 25 years ago. And on the right, there's something that's kind of more like you'd see today. So there is one big difference between this and that. As on the left, you can see the memories. You can see the wires. You can see that they're kind of in the vertical direction on this picture. So that means that they're visible almost by eye. With an optical microscope, you can see these. On the right, there's really nothing to learn from that because it's covered in either a solid metal shield or basically a mesh over the top of the chip. That means that you can't penetrate it. So when I talk about physical shielding, that could be just a blanket of metal or just lines of metal, which aren't really do anything. Or more likely, it'll be an active shield. So this is a mesh running over the top of the chip, and it's being sensed. So there's a signal going from one end of the chip to the other over the top. And if you break a line of that, or the signals don't match up, then it's just going to destroy the device. It's going to dump the flash, and you can't do anything with it. It's dead device. So that's an intentional, effort that the industry's made to make things more difficult for hackers. And on the right, you can see this is actually not a nut cell. I couldn't tell you what it was. Does anybody know what that is? Does anybody? So this is a cell. It will do a function. I think it's a NAND cell. But what if you could make a cell look like a NAND, but it would actually perform as a null, for example? So the reverse engineer is going to look at this and try and work out what function it is. Because it's a component, you can work out what it does. It has to be certain transistors in certain places and connected in a certain way. But what if you could do that and make it appear like something else? Then that's going to confuse things massively. Talk about hundreds of thousands of cells on a device. You could have 20,000 NAND gates, but then half of them aren't actually NAND gates, they're NOR gates. So that would make any analysis of that chip complete garbage. You wouldn't be able to do anything with it. So they do that. They do that now. Some manufacturers actually camouflage cells to make them appear like something else, which is very, very clever and very, very confusing for people trying to reverse. So if you've got a device from back here, back in the 90s, I think this is probably like late 90s. It's not actually a secure device. Nothing was really that secure back in the 90s anyway. But as we can see, the vertical pattern in this logic shows us that we can resolve the metal tracks. So therefore, we could take an optical microscope, which is cheap. We could take many images, we could mosaic them and stitch them all together, and that would be enough resolution to be able to follow tracks from one memory to another, for example. If you can do that, we could deduce that a certain path will carry the data that you want to see. And it's basically a case of using Photoshop, a lot of study, and then essentially you could access the device, a live device, and probe the signal. Is that okay so far? Getting kind of very heavily into the semiconductor side of things, but it's very easy to get lost. So if you have any questions, please just shout up. So yeah, you want to probe the device, but how do you get to it? So you go back to my cross-section image here, and you see this. This is aluminium. This is an aluminium track which is carrying the signal. Above it is glass. If you could remove that glass, you can access the signal, and you can put a needle on it, and that's it. So it's that simple. So you start off with your package. You mask the area that you don't want to attack with nail varnish. That's the weapon of choice usually, because it doesn't get etched by hydrofluoric acid. And then you can drip hydrofluoric acid onto it until you expose and essentially remove this glass covering. Once the aluminium is exposed, you can drop a needle onto it while it's working, and you can extract whatever you want. But it helps if you know where to probe, of course. So back in those days, typical setup would be a chemical cabinet, of course, because you're using hydrofluoric acid, which is probably the worst thing to deal with. Don't start Googling images of hydrofluoric acid burns, for example. It's really not very pleasant, and a lot of people just simply won't use it. It's something that's going to dissolve glass. Imagine something that can actually dissolve sand, and that's nasty stuff. So you need a fume cupboard, and you need to be able to use chemicals carefully. You need an optical microscope, which is nothing, pick them up off the street almost. There's a nice 90s PC for you there, which you'd use your Photoshop on. And ultimately, you want to probe the chip, so there's a probing station with needles. Yeah, you basically open up a hole in the top of the chip, keep it functioning, and you can drop your needle onto wherever you want to go. Obviously, oscilloscope, etc., to analyze the signal or capture the signal. Right, so essentially what has changed. So what happens is the cutting edge geometry of the device is driven by, CPUs, GPUs, video games, machines, servers, so like really high-end applications. We don't need that level of performance in a secure device, for example, not usually anyway. It doesn't have to be that advanced, and they don't want to spend that much anyway. So usually what is being used in secure devices today, that would have been cutting edge maybe 15 years ago. So on the left we have something that was, a valid product in 2003, but that's using technology from maybe 5 or 10 years prior to that. And it's the same these days. This is the device that's used on something quite high end these days. It's a very secure device, but it's using technology from, I'd say, 2007. I think it's a 45 nanometer process on this chip. And that's to do with reliability and the cost, essentially. They don't want to use something that's like 5 nanometer process node because it's just not required. It's too expensive and it's less proven. So to kind of sum up the changes, we have back in the day, back in the 90s, there is no shield, as we talked about, nothing to cover up what is active, what is actually working. Everything you see on there is a functional piece of circuitry which you could access if you want to. The features are large. You can use optical microscope. A maximum of 4 layers of circuitry. So you really, with 4 layers, you can almost follow it. With an optical microscope, you can follow traces from a memory to another. They're robust devices. The features are large. The transistors are strong. You get a clear signal from it, so it's very easy to get a clear square signal and be able to analyze it and reverse it. These days, pretty much everything will have an active shield over the top. So it's not passive, it's actually sensing the device and making sure that nobody's breaking any signals. So you have to get past that. The features are much smaller. Therefore, you can't use an optical microscope anymore. You're just simply not going to see the traces. And I'll go into what we use now, of course, in a bit. Up to 7 layers of circuitry in a secure device, I'd say. CPUs can be up to like 12 layers, I think, these days. But with a kind of an ASIC, something that we've looked at, you're probably up to 7 layers. Maybe 1 or 2 layers would be the active shield, and the rest would be the functional circuitry underneath, carrying the signals. Of course, everything is smaller, transistors are smaller, so it's very sensitive, and you can load the device when you probe it, and essentially you will stop it from working. You need special probing station, special probes that don't kind of overload the device too much. We've got something huge dropping on something which is like 100 nanometers wide. You're probably going to introduce so much capacitance into the device that it's going to stop working. So you need something that's going to be very, very sensitive. It's going to condition and sort of amplify the signal pretty much at the probe point. You have a probe and they have some circuitry which will kind of amplify and condition the signal so you can actually read it or make some sense of it. So I made those 2 points blue for a reason, and that's because of those 2 reasons specifically, that you have to use this thing in the top right hand corner. So where we've gone from basically having quite a basic setup, suddenly you're looking at something like this in the top right. Does anybody know what that is? It's they call it a dual beam. So it's a scanning electron microscope and a focused ion beam in one. It allows you, the scanning electron microscope is to take the images of the device, because you have to do that. You can't do it. The optical microscope isn't powerful enough, so you have to use electrons to take the images to work out what is where, to basically make any sense of anything. So electron microscope has something like a 1 nanometer resolution. The focused ion beam part of it means that you can actually take a live device, you can take that active shield and you can cut it. But once you cut it, you have to repair it, because otherwise the chip is going to know that you've broken it. So what this thing will do, believe it or not, it can cut 2 tracks on the surface of the chip, Then you can access your signal beneath that. After you've accessed that, you can remake the active shield on the surface. So to the chip, it doesn't appear broken. It's like, it doesn't know any better. Nobody's touched it. And depending on the sensitivity of these shields, you have to be very careful how much you can reroute. So really gone from something very basic to something that's, it's almost like science fiction that you're having to do. And also to make sense of the device and try and understand what's happening, you have to be able to deprocess it, because you can no longer just follow a trap with an optical microscope. With this electron microscope, you only see the top layer. You can't penetrate further than that, so you have to image the top layer, remove that somehow, image the next layer down, remove that, and you go down all the way through to the bottom of the device. So that could be 7 layers of circuitry, plus all the vias in between, and all the transistors on the bottom. So you're talking about many layers of images, which can be a lot of work. So I would say for me, the challenge is the deprocessing. Some of the layers between the circuitry are maybe like 200 nanometers thick over something that's 2 millimeters by 2 millimeters. So trying to remove a layer to that precision is incredibly difficult. So you have to invest in more equipment to be able to do that, and more equipment to be able to take the images. So in blue again, obviously this is a expensive piece of equipment, and it's very difficult to use. It's not like anybody can jump on it. Okay, so it's a much broader range of tools are required these days. So to conclude, yeah, anybody, if there is a reward there, it's a no-brainer to just buy the equipment, buy the tools to do the job. The problem is, it's to find the people that can use these tools to effect. The deprocessing tools, the electron microscope, the focused ion beam. It's very niche stuff. You can't just make a lab, buy the equipment, and then just recruit someone. It's not like that. You gotta find the person who can do it, really. And even the dual beam itself, you're talking £200,000 or £300,000 just for the tool, plus £20,000 per year to maintain it. So you need somebody who can look after this thing, use it effectively, and return the investment. And yeah, I think that's the key thing. All the tools are there. Essentially, if you can make something, you have the tools to take it apart. Yeah, it has to be possible to do that. So the tools are all there. It's finding the people that are motivated and can do it. But at the end of the day, it's a machine like any other machine. You can go down to transistor level. Literally could be a million transistors on that chip, but you can get there and you can reverse absolutely everything, because you can't hide anything on a machine. And it's basically a machine, but it's very, very difficult work. Was that 30 minutes? I don't think it was really, was it? Yeah, please. Interested? Well, that's another thing, is people, it's very secretive, like a lot of things. Okay, so if somebody develops a technique to deprocess a device, a small geometry device, they're not going to post that on the internet and show everybody how to do it. They want to keep their IP to themselves. Whether you're a hacker or you're a legitimate reverse engineer or you're a penetration tester, you want to keep your techniques to yourself. So there are some sites, but they tend to focus on very old devices, which are easy to, but then it gives the same outline of what is required. You just need different tools nowadays to what you'd attack sort of 30 years. And these people are mostly hobbyists, so they're not going to have like a £200,000-300,000 focused ion beam in the back, in the kitchen or garage or whatever. But I would say, I mean, I'm a chemist by sort of education, so I have technically no experience in electronics at all. But in the manufacture of semiconductors and the reverse engineers of semiconductors, there's an awful lot of chemistry involved. So you could, a background in chemistry or physics would be beneficial, but I mean, it's really the person at the end of the day. But there are, it's, again, if you're trying to research something, certain things, certain terms that you need to be looking for. But there's not a lot, especially when it comes to sort of working on more modern devices. Mm. You need, that's another massive investment as well as the software, because you can't just like chunk everything into Photoshop. If it's like 30 or 40 gigabytes per layer, then it has to be aligned, and then you have to be able to, it'll allow you to kind of follow signals on the device, but it doesn't really allow you to fully reverse engineer the device. To fully reverse engineer it, you need to go down to transistor level and logic gate, logic cell level. So yeah, what you would do is you would take the images from the bottom of the device, you go cell by cell. So you take the first cell and you would reverse that yourself just by knowledge of electronics and say, okay, that's a null. And you would label that as a null. And you need the software, you need custom software, you need to be able to build software yourself or work somewhere where they will build something for you. So what they will do then is you give that a name, you mark the inputs and the outputs, but then you tell the software to recognize every instance of that cell in that sea of logic. Once it's done that, you go on to the next one, and then you could be going up to like 300 gates to reverse engineer. But then ultimately you will have the full functionality of the chip reversed. You'll have the inputs and the outputs for every single cell. Sorry. So if you know the input and the output of every cell, then the layers above that are just transport for those signals. So you just need to kind of wire up. Like say it's a machine, you've got logic cells, and you got wiring to connect it all up. And then from the wiring, you'll see what goes to the flash, what goes to the ROM, and you kind of make your hypothesis from there. Yeah. Sorry, I'll let you go first. As you. Yeah, I guess. I mean, there's a lot of potential, I think. Yeah. I mean, think from essentially you need to get those layers. It's kind of easy. You can apply a lot of things if you get perfect images from each layer, and that for me is the challenge. If you had a machine where you could just put this chip in and suddenly it spits out, every image from every single layer, that would be like great. People, yeah. Yeah. Oh, absolutely, yeah. Exactly, yeah. I mean, certain things you need to recognize at the cell level. You have the substrate of the silicon, and then you have the polysilicon on top of that, which is conductive, and that joins the kind of the PMOS to the NMOS. You have the contacts, and you have the metal above that, which is like the internal wiring for the cell. And if you have those images, yeah, instead of just trying to reverse it yourself or trying to make sense of it yourself, yeah, of course you could teach. Yeah, exactly. Yeah. Red jacket. Uh, why? Sorry, why? Okay, so my old company, they were built on home computer accessories, like back in the 80s, and then with video games, they tagged onto that market. And in the start, there was not a lot of security on video games, like PlayStation 1, for example. We were talking about it earlier, and the only kind of thing that stopped people making games was they put a special mark on the CD, which a normal CD player or a CD reader wouldn't see. PS1 would look for this mark to make an assumption that it's a legitimate Sony product. So it's outside of the normal region of CDs. It wasn't in the kind of the manual of CD manufacture. It was a special thing that they added. But once you found that, you could make your own discs for PS1. So That's how my old employer basically got into the video game market. From then on, it's got more and more difficult. Instead of putting it on a disc, like you making a special disc, they'll put a solution on the they'll put a chip in the accessory, which is only there to kind of maintain the security between the console and the accessory. They do that because they only want to sell accessories. They don't want anybody else to sell accessories. So if you have the ability to reverse engineer that chip, you can then make controllers for PS5, for example, and that'll be pretty lucrative. And the same with the ink. Ink market is the same. It's revenue protection systems, basically. You want to sell ink. You're not putting that chip on because it can measure the ink in the cartridge or anything else. It's basically just securing your future revenue. Well, if I was HP, I would be, well, you get approached by some, I'll say in the last 5 years, I was doing more security evaluations. So you have a manufacturer come to you and say, look, this device is out in the wild now. How long is it going to be secure for, in your opinion? So we do the penetration test on this device. Say, okay, this is how long it would take. This is how much expertise is required. This is how much tooling is required. And basically go back and say, okay, you can rely on your, 100% income from ink for like 3 years or 4 years. And they would just try and do the best they can. Then they can plan their next generation of devices already in development, but they're trying to kind of financially plan for the future and just competitors, yeah. Yeah, it's just people that want to sell ink or video game accessories, yeah. But if you can, there's multi-billion-dollar companies making third-party ink, for example. I mean, it's insane. You wouldn't imagine, but it's crazy. And there's many of these companies, and they're all fighting to be the first provider for a specific solution. If you could hack the latest HP printer cartridge, you'd literally be a billionaire within a few months because nobody's done it yet.
Ship such reverse engineering because we were talking 1 to 2 mil squares. Because they marry zone just busted billion to billion. But sure, you make a billion plus.
Yeah. It's forced people to get into the focused ion beam side of things, which is a big step up. Before it was an optical microscope that might be like a few £1,000. Suddenly you've got this dual beam instrument which you've got to maintain. It's going to cost, if you want to buy a new one, it's like £1.5 million. You can pick up a used one for £200,000, £300,000, but then there's like at least £20,000 every year to maintain it. So I suppose it scares people, I guess. You kind of eliminating a lot of people that aren't that serious, I suppose. It's maybe a smaller kind of spearhead of people that are really intent on doing this.
Thank you, everybody, for coming. If you want to talk to Tony, obviously he'll be here. And we do the Hack SOHO, barring any new phenomena that we'll do every month. So you guys are welcome to come back, and appreciate everyone's time coming here. So thank you. Thank you, Tony.